At absolute zero, 0 Kelvin, heat completely vanishes. In classical physics, this is the cosmic speed limit for cold, where all thermal energy dissipates and every atom grinds to a dead stop. Everyday gases, like the oxygen and nitrogen we breathe, freeze into solid chunks of ice long before they ever reach this extreme temperature. But drop liquid helium to exactly absolute zero, and it completely ignores the cold. It remains a sloshing fluid liquid. If every element in the universe succumbs to the cold and locks into a stationary grid, why does helium refuse to freeze? This behavior points to a massive gap in how classical physics explains matter at the extremes of the universe. Freezing is a microscopic tug-of-war. Kinetic energy pushes atoms apart, while weak van der Waals forces act as a tether pulling them together. When heat is removed, kinetic energy disappears. The attractive tethers win, and the atoms snap together into a rigid solid. But Werner Heisenberg and quantum mechanics ruin this perfectly clean mathematical picture. His uncertainty principle dictates that an atom can never have an exact position and zero momentum at the exact same time. Matter must retain a baseline vibration, known as zero-point motion, even at absolute zero. Helium atoms have incredibly low mass and hold their 2 electrons very tightly to their nucleus. This structural combination gives helium the absolute weakest van der Waals tethers of any element in the periodic table. This animated chart illustrates the resulting imbalance in helium-4. The towering column shows the quantum zero-point kinetic energy, which is 7 times stronger than the tiny measure of atomic glue trying to hold the atoms together. Because of this, quantum mechanics acts as a literal wrecking ball. The helium atoms violently vibrate themselves right out of any solid lattice, overpower over rules of classical thermodynamics. Because standard freezing is blocked, dropping helium-4 below 2.17 Kelvin, the lambda point, forces it into an entirely different state, a quantum superfluid called helium-2. Helium-2 operates with exactly 0 viscosity. Without friction, the fluid creeps up the inner wall of a glass container and pours itself over. To force helium into a solid, scientists have to cheat the temperature scale and use external pressure. Applying 2.5 megapascals, roughly 25 times standard atmospheric pressure, physically crushes the wildly vibrating atoms together, restricting their spatial uncertainty just enough to force a crystalline grid. The lighter isotope, helium-3, exhibits an even stranger behavior known as the Pomeranchuk effect. Solid helium-3 actually has higher nuclear spin entropy, meaning it has more internal atomic disorder, than its liquid form. Because thermodynamics naturally favors higher entropy, applying heat under specific pressures actually forces liquid helium-3 to freeze into a solid. Helium completely abandons standard temperature-based freezing rules. Trapping it as a solid requires either bone-crushing pressure or entirely counterintuitive heating. This stubborn refusal to freeze makes liquid helium the ultimate stable cryogenic coolant. Because it won't solidify and block vital cooling channels, liquid helium is the essential lifeblood for keeping massive superconducting magnets stable in everyday medical technology, like MRI machines. It operates on a massive scale, too, chilling the primary magnets inside the most advanced particle accelerators in the world. Mankind's ability to peer safely inside the human body or discover foundational particles at the edge of physics relies entirely on exploiting this specific quantum loophole. At its deepest microscopic foundation, the universe absolutely refuses to sit perfectly still. Helium is simply the only element that refuses to hide that fact from the naked eye.